Hi scientists, today we're going to be talking about acids, bases, and the pH scale. This relates to our current chapter because we want to think about our bodies having the correct pH in different parts of them. We know that enzymes work only in certain pH levels, so depending on what the pH of our body is or the acidity of a different part of our body, that will determine what enzymes can work there. This also relates to homeostasis because our body works to keep the proper acidity or pH in different areas of our body and to keep that stable. So here in this chart we have a few examples of acids, and I'd like you to take a minute to pause the video and see what patterns you can come up with. What things are the same for all these compounds? So you might have decided that they all have acid in their name, and the first part of the name ends with IC, so like hydrochloric acid, nitric acid. They all have a hydrogen in their chemical formula, and they all form the ion H+1 in solution. That's going to lead us to our definition of an acid. So there are a few different definitions for acids and bases. In this class, we're going to use Arrhenius's definition. And Arrhenius said that acids are substances that break apart in solution to add an H+1 ion. So when we dissolve an acid, one of the ions it breaks apart into is the hydrogen ion. Acids taste sour. Strong acids are corrosive. And then they have this property, of course, that in solution they form H+1. And some examples, which we saw on the previous slide, are stomach acid, which is hydrochloric acid, acid rain, battery acid, citrus fruit, and vinegar. Here we have a chart with a few examples of bases. So again, take a minute to pause the video and see what patterns you come up with. Bases, we see that they don't have the word base in their name, which can make them a little trickier to identify. You might have noticed that many of them are cleaning products, and then in solution they have OH-1 ions. You might also have noticed that some of them have the name hydroxide, and if we're translating our chemical formulas, you might decide that hydroxide means OH, and you would be correct, right? When we see sodium hydroxide, and then we see NaOH. And that, of course, is our Arrhenius definition of a base. Arrhenius said that bases are substances that add OH-1 or hydroxide ions to an aqueous solution. So when we dissolve a base in water, it splits apart and forms an OH-1 or hydroxide ion. Some properties of bases are that they taste bitter, strong bases are corrosive, they can feel slippery, they react with fat to make soap, and of course they break apart in solution to form OH-1. So one fun experiment you can do at home to understand how bases react with fat to make soap. A good example of a base is baking soda, and if you wash your hands with just a little bit of baking soda and plenty of water, you can feel that it's reacting away the fat in your hands. Your hands will feel really nice in the beginning, and then they'll begin to feel a bit dry as they realize that all the oil has reacted away. So get some hand cream after. So some examples of bases are drain cleaner, baking soda, lye, antacid tablets, and window cleaner. Scientists classify acids and bases through the pH scale. So it is a scale from 0 to 14 that describes how many H+1 ions there are in a particular substance. So acids are on the range from 0 to 6, neutral substances like water are 7, and then bases are 8 to 14. And so on the far ends of the scale we have strong acids and strong bases, and then closer to neutral we have what we call weak acids and weak bases. And this has to do with the properties of the acids or the bases. So a strong acid would be very sour, a weak acid would be slightly sour. A really strong base would be very corrosive, a weak base would not be very corrosive. So the stronger of an acid or base we have, the greater the properties are. So the more H+1, the lower the pH, and the more acidic the substance is. In the definition here I have the word logarithmic, which might be a new word to you, so we'll take a minute to talk about that, or you may have heard about it in math class and be very familiar with it. So A linear scale would be a scale that goes up by 1 in each direction. And a logarithmic scale is one that goes up by 1 in one direction, but goes up by 10 in the other, for a log-base 10 scale. Here's what pH is. So every unit of change in pH represents a tenfold difference in how much H+1 we have. So for example, a solution that has pH 3, or that is pH 3, has 10 times less hydrogen than a solution with pH 2. And a solution with pH 4 would have 10 times less hydrogen than that. So the pH units are changing by 1, and the concentration of hydrogen is changing by 10. I popped this graph in here not because it's that useful, because the scale isn't great, but just you might remember what it might be a helpful reminder what a log function looks like, or an exponential function looks like from math class. And then we won't be doing any math with this for this chapter, but I popped the equation in here as well. So pH is equal to the negative log of the hydrogen ion concentration. So if you were going to plug hydrogen concentration into your calculator to calculate the pH, you would use the log button and then take the negative of that. Okay, so that's it for today. If you have any questions, please leave them in the comments below or stop by office hours.